Assalamu alaikum everyone. This is the second lecture on the insulators in the mechanical design of the transmission lines, and in the last lecture we actually talked about different type of insulators, which includes the pin insulator, the string insulators, and then shackle insulators. And in the last portion of the last lecture we were talking about the string efficiency of the suspension insulator string. In that we talked about two different type of capacitances. The first one was the self or mutual capacitance. If we have three discs in a string, then it can be represented by three capacitance values, and we have a current that is flowing from conductor towards a grounded tower. So this is your grounded tower and this is your conductor. So conductor is placed at the bottom of the string of insulators, and this capacitance, it is actually due to the metal fitting, and then there is an insulator, then there is another metal fitting, so it forms a capacitor. Then we concluded that if we only have the self or mutual capacitance, then the voltage is divided equally along the suspension insulator string, and each capacitance or each disc has equal voltage. So if we have three different discs, then the voltage is divided into three equal parts. Now the second capacitance that we talked about was the shunt capacitance, and it is between the metal fitting and the tower. So this is the point where we have metal fitting and this is your tower, right? So the capacitance, the shunt capacitance, that is actually between the metal fitting and the tower, which is grounded. This is C1, and if I have to define that what is the effect of this shunt capacitance, it will reduce the current that is moving towards the grounded tower from the conductor. So there is a portion of current that is passing through these C1s, which are the shunt capacitances. So the current through the capacitances that are the self capacitances is not equal. Because of that, the voltage across all the discs is not equal. And by explaining these two capacitances, there are few important points that we concluded about. The first one was that voltage across all the capacitances was not same because of that shunt capacitance. Before that, if we are only considering the self capacitance, the voltages were equal. The second point is that the maximum voltage will be across the insulator that is closest to the conductor, because it has the maximum current I3 that is passing through that, and as the current moves away from the conductor, move towards the grounded tower, the current will start reducing because of the leakage current through the shunt capacitance. So these are the few points that we discussed in the last lecture. Now moving on towards the string efficiency of the string insulators. This is the today's topic, and by definition, string efficiency is just the ratio of the voltage across the string, and voltage across the string in this case is V. That is the voltage starting from the grounded tower, and till the conductor. So this is the voltage V. So in the numerator we have voltage across the string, and in the denominator we have N is the number of discs in the string. In previous case we have three discs, 1, 2 and 3. So in this case N is equal to 3, and in denominator we have voltage across disc nearest to the conductor. So this is the largest voltage which is across the disc which is closest to the conductor. Now if I have to define the string efficiency, it just defines the distribution of voltage across the string insulators, right? So if the string efficiency is larger, then the voltage distribution across the string, like there we have three different insulators. If the string efficiency is larger, in this case string efficiency is larger, it means that the voltage distribution among all the discs will be equal or will be almost equal. So if string efficiency is larger, so V1 will be approximately equal to V2, approximately equal to V3. So what we need is that ideally we want the string efficiency to be equal to 100%, ideally. and by 100% we mean that the voltage is equally distributed among all the disks. So V1 will be equal to V2 will be equal to V3. So this is the concept of string efficiency, and we want to increase the string efficiency. Because of that we have uniform voltage distribution along the disks, and ideally it is uniformly distributed if the string efficiency is maximum, which is 100%. Now if I have to derive the formulas for voltages V1, V2 and V3, that are the voltages across the string insulators, and we have 3 disks, 1, 2 and 3. This is disk number 1, there is another disk here 2, and then there is another disk here 3. So we have 3 disks. The voltages across the disks are V1, V2 and V3. So what we want to find these voltages V1, V2 and V3. Now we will be starting from node A. So I will be defining this node as A and this node will be B. So if I have to find V1, I will start by applying KCL at node A. So Kirchhoff current law, it says that the current I2 will be equal to I1 plus I1. So this is the summation of the current that are moving away from the node A, which will be equal to the current I2 which is moving towards the node A. So now if I have to find the current I2, this is the current I2. So this current I2 will be equal to the voltage across this disk, which is V2, and the capacitive reactance of the particular disk. So what if I have to find the current I2, it will be the voltage over capacitive reactance. So the capacitive reactance is 1 over omega C. It will be equal to V2 omega C. This is I2. Similarly, I can find the current value I1, which is across C1, and then I1 which is across the self capacitance C. So equation 1 will be V2 omega C, which is equal to I2. Voltage across the capacitance is V2 and the capacitive reactance is omega C. C is the capacitance, self capacitance. For I1, again the voltage will be V1 omega C 1 plus V1 omega C, right? So the voltage across the self capacitance is V1, and for current I1 it will be multiplied by omega C, and for the shunt branch currents we have V1 omega C 1. Now this is the KCL applied at node A, right? Now if we assume that we are assuming that C1 is equal to KC. So this is your shunt capacitance, right? And this is your self capacitance. So the shunt capacitance is a smaller value than the self capacitance. So this C1 is actually the fraction of the self capacitance, right? So if I will use this C1 in the equation that I derived above, then the equation will become V2 omega C is equal to V1 omega C plus V1 K omega C, right? So what I have done, I have just replaced this C1 with KC, and after solving it will become V2 omega C is equal to V1 omega C into 1 plus K. Omega C will cancel out and V2 is equal to V1 1 plus K. So this is the voltage V2 across disk 2. Similarly, if I have to find the voltage V3, that will be found by applying KCL at node B. So we have node B at this point. So KCL at node B. So the current I3 is entering into node B, and the current I2 and I2 is moving away from the node B. So by KCL we can write I3 is equal to I2 plus smaller I2. And similarly again, if I have to find the currents, I3 will be this current, and the voltage across this capacitance is V3, and the capacitive reactance will be omega C. So I3 will become V3 omega C. For I2, this will be the voltage across the capacitance is V2 and capacitive reactance is omega C. So this will become V2 omega C. Now for the current I2, we have to find the current in this branch, right? So the voltage across this branch will be the same voltage that is from this point B to the grounded tower. So the voltage from point B to this point will be same as from point B to the grounded tower. So what is the voltage across from point B to grounded tower? That is V1 plus V2 omega C1. So this is your current I2. So after solving, this will become V3 omega C is equal to V2 omega C plus V1 into 1 plus K omega C1. So now we also know that C1, which is the shunt capacitance, it is the fraction of the self capacitance. So I will use this formula in the above equation. So the equation will become V3 omega C is equal to V2 omega C plus KV1 plus KV1 into 1 plus K into omega C. And these omega C will cancel out with the omega C on the other side of the equality, and V3 will be equal to V2 plus KV1 plus KV1 plus K square V1, right? But we also know the value of V2, so I will use this value V2 in this equation. So V3 will become V3 is equal to V1 into 1 plus K plus KV1 plus KV1 plus K square V1. By further solving, it will become V1 plus V1K plus V1K plus V1K square. So the final equation will be V3 is equal to V1 into 1 plus 3K plus K square. So this is your second equation. So what we have done, we have found out the two equations, two voltage values V2 and V3 in terms of voltage V1, and both the voltages V2 and V3 are related to the voltage V1, which is across the insulator which is closest to the grounded tower, by a constant K, which actually is a relationship between the shunt capacitance and the self capacitance. So now if I have to find the total voltage V, that will be equal to V1 plus V2 plus V3, right? So this V is actually the voltage at node C, right? So if I have to find the voltage at node C, this is just the summation of all the voltages V1, V2 and V3. At node C we have a conductor, and at this point we have a grounded tower. So if I have to find the voltage at node C, it is just the summation of all the voltages V1, V2 and V3. So if I will write it down, this is the voltage at node C. So it is just the summation of all the voltages. So we know that V1 is V1, but V2 is equal to V1 into 1 plus K plus V3 is this one. So V1 into 1 plus 3K plus K square, right? And V is equal to V1 into K square plus 4K plus 3. So this will be the final equation after solving the equation that was written above. So this is your equation number 3. So from equation 1, 2 and 3 we can write that from equation 1, 2 and 3, we will have an equation which is V1 is equal to V2 over 1 plus K is equal to V3 over 1 plus 3K plus K square is equal to V over K square plus 4K plus 3. This equation shows the relationship between the voltages across the individual discs of the string insulator. So now if I have to find the string efficiency for this particular case, string efficiency, and from formula we know that string efficiency is actually equal to voltage across the string divided by the multiplication of total number of discs into voltage across the disc which is nearest to the conductor. So voltage across the string is actually V. What is the total number of disc? It is 3, and voltage across the disc nearest to the conductor is V3, and efficiency is in percentage, so it is into 100. So this is the string efficiency for this particular example. So from the above discussion we can summarize few important points, which are: for the first point, we will make an assumption. Assume we have the value of K is equal to 0.2. So for the values of V2 and V3, we have already found out the formulas, and the value of V2 will be 1.2 V1 and the value of V3 will be 1.64 V1. So it just shows you that as we are moving towards the conductor, because V1 is closest to the tower and V3 is closest to the conductor. So as we are moving away from the grounded tower and moving towards the conductor, the voltage stress over the insulator disc is increasing. So closer to the grounded tower we have voltage which is V1. If we move away for the second insulator, we have insulating disc, we have V2 which is equal to 1.2 V1, and for the third one which is closest to the conductor, the voltage stress is highest, which is 1.64 times the voltage across the first disc which is closest to the grounded tower. Now there is one more point that can be derived from the equations of the voltages, that the voltage value is actually dependent on the constant K, and this constant K is just the relationship of the shunt capacitance and the self capacitance, right? So the voltage distribution it depends on the value of K, and if the value of K is larger, the non-uniformity will be larger. Now by non-uniformity we means that the voltage distribution across all the insulating disc will not be equal, right? So if we have to increase the string efficiency, so what we have to do, we have to reduce the value of K, right? So the voltages across all the discs V1, V2 and V3, they are dependent on the value of K. So if the value of K is larger, the non-uniformity or voltage distribution across all the discs will not be same. So if we have to make it same or equal, what we have to do, we have to decrease the value of K, and if we are decreasing the value of K, the string efficiency will be increasing.